So, in this video, I will share with you what I learned regarding the Hurst exponent of 0.1. It is a discovery that changed options pricing forever. So, we'll be exploring a paradigm shift in the financial mathematics. Volatility is rough. As you can see on the screen, we are redefining market dynamics at high resolution, moving away from the smooth waves of classical theory and into the highly jagged, fluctuating reality of actual market data. So, to understand this shift, we must have to recognize the macro illusion. Classical models rely on the Brownian assumption, predicting standard diffusion processes and square root of time scaling. However, the macroscopic reality reveals a high frequency anomaly. Modern tick data shows fluctuations that are far too extreme and fast, mathematically failing the standard rules. So this brings us to the geometry of noise and the concept of the Holder continuity. The Holder continuity defines path regularity. So essentially, exactly how wildly a stochastic process fluctuates in the blink of an eye. While the standard Brownian motions, where the Hertz exponent is equal to 0.5, it forces the standard deviation of paths to scale by the square root. Fractal Brownian motion with Hertz exponent of 0.08, so less than 0.5, it scales by the h. This proves that the market does not follow the square root time rule. Instead, short-term variance is inherently explosive. That's why there are like the sudden spikes. So you can think of the Hertz component as the dial for the market's roughness. If we turn it up at 0.8, we get a smooth, trending and persistent path. At 0.5, we sit at the classical standard Brownian motion baseline. But when we turn the dial down to 0.08, we generate explosive short-term variance that truly mimics the high-frequency reality. The data demands we turn this dial all the way down. So, and this is, it's not just theoretical, it is an empirical reality. When we analyze the data, we find a universal constant. Looking at the scaling of volatility across time intervals, whether we tag the S&P 500 at 0.13, the DAX futures at 0.14, or the Nasdaq at 0.15, the results are remarkably consistent. Because across millions of high-frequency data points and distinct asset classes, the estimated Hertz parameter stabilizes universally around 0.1, proving that volatility is fundamentally rough. So this roughness directly solves the implied volatility anomaly. A known fact in the equity index options is that the implied volatility skew steepens aggressively at the shorter maturities. Classical Brownian motion models fail completely here, falsely predicting that the time to maturity approaches zero, the at the money skew flattens out, which is not the case, because the market reality quotes a curve that explodes upward near expiration, Geometry, classical models are fundamentally blind to this concept. So this is how exactly the roughness fixes the math. The first step is identifies that the slope of the at-the-money volatility skew obeys a negative power law relative to time to maturity. Step 2 gives us the formula. The slope is proportional to TH minus 0.5. Step 3 is the exponent resolution. So if h is 0.5, as in the classical models, the exponent is 0. This becomes 0. So this becomes 1. So the slope is completely flat. But if we plug the realistic h exponent or the Hurst exponent of 0.1, this becomes minus 0.4, which would cause the slope to steepen towards infinity. So by plugging this into the fractional stochastic volatility model, we perfectly generate the exact extreme short-dated smiles seen in real trading with zero jumps required. Moreover, the roughness resolves the long memory mirage. So for decades, the volatility persistence was considered stylized fact, but it is actually a statistical trap. The true microscopic source isn't dense. Short-term volatility fluctuations characterized by negative serial correlation. When classical econometrics tests analyze the autocovariance over long lags, they falsely detect an autocovariance decay, creating a false, let's say, artifact. The volatility is not a long memory process, but the perceived long memory is a mathematical illusion generated by the underlying high-frequency roughness. To summarize, let's look at the volatility paradigm matrix. We're moving decisively from the classical era to the rough era. The path regularity shifts from smooth to fractal and explosive. The short-term at-the-money skew no longer flattens, it steepens. Instead of requiring heavy calibration with many parameters, our models becomes like just driven by the Hurst exponent. And finally, out of the sample, forecasting moves from poor forecasting to superior that consistently outperforms the classical era. So what is the pragmatic payoff, or why must traders care? First, avoiding the structural arbitrage. If your pricing model assumes a smoothness greater than the market's true roughness, you will inherently misprice short-term options, because rough models protect the delta hedge from arbitrage exploitation. Second, superior forecasting. Rough fractional stochastic volatility models drastically outperform standard models across almost all stock indices and horizons. And third, the one parameter edge. So instead of overfitting the complex multi-parameter models, forecasting collapses into estimating essentially one universal parameter, the Hurst index H. So, in conclusion, we must embrace the noise. The market is not smooth, continuous machine. It is fundamentally fractal and rough at its core. By abandoning the illusion of classical Brownian motion and turning the roughness dial down to reality at h about zero point 0.1, we unlock the true geometry of risk, exact pricing of the volatility surface, and a decisive edge in out of sample forecasting.